Is the cost of space exploration really worthwhile? It's a question that crops up regularly. Could the money be better spent elsewhere? Even if it were, one space program would still have to remain in place. That's the Planetary Defense Program, to locate, identify and deflect any wayward asteroid from hitting Earth and destroying our civilization. At the last count, there were 15,000 potentially dangerous candidates close to Earth. It's now over 2 years since the Rosetta mission reached its target rendezvous, 67P. It's been an audacious mission, gaining unprecedented forensic knowledge of the comet's surface, interior structure, composition and history.
We've noticed that there is not ice on the surface. We would be able to see that, at least not large patches of ice. You don't have skating rinks on this comet. And we also see gas in the coma. We see evidence of carbon monoxide and carbon dioxide and the elements themselves of carbon and oxygen in different parts of the coma.
And we discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
In particular, what we have observed is that the nucleus is composed of a mixture of materials like minerals, like silicates and sulfides, which have been formed in the inner part of the solar system, close to the sun.
Because the comet is kept in a very cold environment, we don't expect it to have very high temperature phases, so it can be that this material was formed closer to the sun and was then brought to the comet later. And this for us was a surprise because we knew it for the minerals but not so much for the organics. So it seems that the organics also can be transported over large distances in the solar system.
The most prominent, the most exciting changes on the surface, I believe it is still the big drop in the Imhotep plateau, which was 3 meters and 100 meters in height and hundreds of meters in radius. But we have seen smaller scale features like a boulder, which was at least 50 meters big. It was 10 tons heavy, which, well, on the comet is just a chocolate bar of 100 grams or so, but still it's a massive thing, which has moved by 140 meters, likely due to activity, but we don't know the real reason.
It was time to decide what to do with Rosetta now its mission was complete. One option was to land it on the comet.
There were discussions about what would be the priority for the end of missions. So there were several scenarios put together, and one of the options was to do those very close flyovers. And I mean, in terms of the science objectives, that was the one that will bring us the more interesting scientific results. So it was decided by the science working team to go for this scenario. So yes, that's a very first, again, another first of Rosetta.
Rosetta's trajectory was altered to spiral into the comet, taking photos as it closed in.
Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data. So the spacecraft may end, but the science will continue. That's what we're here for. That's what this mission was for.
We just have had a loss of signal at the expected time. This is another outstanding performance from flight dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
One major problem faced by Rosetta and its Philae lander was low gravity. When the lander's harpoons failed to secure it to the comet, it tumbled and bounced until it was lost in the rugged terrain. But engineers love a challenge, and they have already come up with a novel answer for next time. It's called the Hedgehog.
So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we have flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly.
JAXA's sample mission from asteroid Itokawa from the last decade returned mixed results. It did, however, teach engineers and designers many lessons about the difficulties of collecting samples from asteroids. Their second attempt is currently underway. Hayabusa 2 is coasting towards another asteroid, Ryugu, and should reach its destination in the middle of next year. This new and improved robot has several new capabilities built in. They include ion engines, navigation and attitude control systems, and an explosive device to dig into the asteroid and return material from within it. Also on board are a probe and 3 miniature rovers. A secondary probe launched with Hayabusa, called Procyon, had an engine malfunction and will not complete its mission. NASA's attempt at an asteroid sample return is also underway. OSIRIS-REx was launched from Cape Canaveral Air Force Station's Space Launch Complex 41 and is on its way to intercept the near-Earth object Bennu.
2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bennu is a B-type asteroid of approximately 500 meters diameter. It completes an orbit around the Sun every 1.2 years, and every 6 years it comes very close to Earth. These close encounters mean there is a high probability of Bennu's impacting Earth in the late 22nd century. Bennu's size, primitive composition, and potentially hazardous orbit make it the ideal OSIRIS-REx target asteroid. It will first survey the asteroid to find an ideal touchdown site.
Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample.
The 7-year mission will see OSIRIS-REx touch down for only a moment to retrieve a surface sample of the asteroid, then return to Earth to deposit the sample return capsule somewhere in Utah in 2023. NEOWISE has been a reliable workhorse, operating long past its planned lifetime, but its mission will eventually come to an end. Engineers estimate it will move into too much sunlight to function. However, the team is eyeing a new space telescope, one with a little more muscle. The Near-Earth Object Camera, NEOCAM, is specifically designed to hunt asteroids. The proposal has been funded for further study by NASA. Undergoing preliminary work is the Asteroid Impact Mission, AIM, whose launch could come as soon as 2020. A joint NASA-ESA project would see ESA launch AIM to a binary asteroid, Didymos, and its satellite, Didymoon. They were discovered over 20 years ago and are part of a group of asteroids called the Apollo Group, near-Earth objects that cross Earth's orbit and are a potential threat. ESA's part of the mission is to orbit and study the asteroids, in particular their orbits around each other.
AIM will rendezvous with asteroid Didymos in June 2022. The first thing it will do is to take high-resolution images so that we can reconstruct a 3D shape of the moon. and then we will use this data to test a new optical communication system with a laser transmitting these images down to Earth in a very quick way. After we do these measurements and we have the 3D model, we will sound the interior structure of the asteroid by deploying a small microlander on its surface that will emit small radio waves that will be captured by AIM and reconstruct the interior structure. After we have done these measurements, the spacecraft will move away about 100 kilometers from the system, waiting for DART to arrive and impact the Moon.
NASA's contribution DART is a kinetic impactor traveling at 6 kilometers per second.
Once the impact has occurred, then we will look at the ejecta and the dynamics of the ejecta cloud. We'll come closer to the Moon and repeat the same sets of measurements so that we can understand the changes in the interior structure and the shape and the morphology of the crater before and after the impact. AIM is the first mission to test the kinetic impact deflection technique. It's the first mission that will prove deep space optical communication systems, and it's the first mission to deploy CubeSats in this space and test intersatellite communication systems. Also will be the first mission to rendezvous with a binary asteroid and characterize it so that we can understand how these bodies are formed, which is highly linked to the way the solar system has formed.
By measuring Didymoon's physical properties and its orbit before and after DART's impact, scientists will gain valuable knowledge that can be applied to a real threat should it ever occur. NASA is proceeding with long-term goals such as a manned sample return from an asteroid. A robotic spacecraft would locate and capture a small asteroid and redirect it into a lunar orbit. An Orion capsule would then rendezvous with it. Astronauts are now training and developing techniques for such a complex mission. There are still many things to be learned about asteroids and the dangers they might pose. As this animation shows, the inner solar system is awash with asteroids. Many of them are near Earth's orbit. Some even cross our path from time to time. All these possible hazards need to be identified, their orbits must be calculated to a high degree, and their threat assessed. Finally, we need to develop the technology to mitigate any danger to our planet. There are several groups of asteroids based on where they orbit. Those within Earth's orbit are Atens and Amors, while the Apollos cross Earth orbit. The majority of asteroids reside in the main asteroid belt between Mars and Jupiter. Then there are the Trojans, trapped within Jupiter's gravitational pull. And beyond that, other remnants of the solar system's formation can be found caught in the orbit of Uranus. There is a great deal more to be learned and understood about these other asteroids. To this end, 2 new asteroid missions have been planned and funded through the development stage. They will study 2 very different types of asteroid. The first of those missions is Lucy, which will visit a target-rich environment of Jupiter's mysterious Trojan asteroids. The mission will launch in October 2021 and fly by its targets between 2025 and 2033. In all, Lucy will study 6 Trojans and 1 main belt asteroid. Trojans are fossils of planet formation, and so will supply important clues to the earliest history of the solar system. The second is Psyche. This mission will explore one of the most intriguing targets in the main asteroid belt, a giant metal asteroid known as 16 Psyche. About 3 times farther away from the Sun than the Earth is, this asteroid measures about 210 kilometers in diameter, and unlike most other asteroids, which are rocky or icy bodies, is thought to comprise mostly metallic iron and nickel, similar to Earth's core. Psyche could possibly be the exposed core of an early planet, which lost its rocky outer layers in violent collisions billions of years ago. The mission will help scientists understand how planets and other bodies separated into their various layers: cores, mantles, and crusts. Psyche will map features, structure, composition, and magnetic field, and examine a landscape unlike anything explored before. For an instrument first developed as recently as the 17th century, the telescope has traveled a long way. The latest version of the once Hubble Telescope will be going a lot farther, carrying us ever closer to the first light that ever bathed the universe in which we live. Generational change is part and parcel of our lives. In terms of space exploration, the Hubble Space Telescope has been doing its extraordinary work for a generation now, and it's time to hand over the reins.
What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything.
Galileo, Herschel, Hubble. Our knowledge of space is marked by some of the greatest names in the human history of stargazing. But who was James Webb? His name is attached to the James Webb Space Telescope, which will soon be helping us understand what lies beyond even the amazing reach of Hubble. Originally called the Next Generation Space Telescope, Hubble's successor was renamed in 2002 to honor James E. Webb, who ran NASA from February 1961 to October 1968. Those dates, of course, put Webb at the heart of the American space program, and the moon landing in particular. But that was not Webb's sole preoccupation. Webb's energy encompassed robotic spacecraft, probes to Mars and Venus, and in 1965, his advocacy of a large space telescope. He was, in other words, a man of vision. The James Webb Space Telescope is nearing completion, in readiness for a scheduled launch in October 2018. By a happy coincidence, exactly 50 years since James Webb's tenure at NASA ended. Its aim is modest, to study every phase in the history of the universe. Several major agencies have collaborated in the creation of the James Webb Space Telescope. NASA's Goddard Space Flight Center is at the hub. ESA will provide the launch vehicle, the ultra-reliable Ariane 5 rocket. Canada's space agency is involved, as is the Space Telescope Science Institute, while Northrop Grumman is the chief contractor.
The Webb will be wonderful for the astronomy community. Not only will it give them the kinds of wonderful resolution we have with Hubble that you can get above the atmosphere, but it's going to bring them access to a wavelength region where many of them have not worked before.
We have a telescope that's far more powerful than anything that we have had before, working at infrared wavelengths, which you can't see well from the ground. And that will enable us to see things from the most distant universe that we can only guess at, things in the outer solar system that we can only guess at.
The Webb is going to be such a powerful telescope. It's going to be like the Hubble. And in the case of the Hubble, probably more than half of the greatest observations, discoveries that the Hubble made were things people didn't anticipate. I expect the same for the Webb.
The James Webb Space Telescope's mission duration is a planned 10 years, during which it has a number of specific goals to accomplish. It will search for the first galaxies, determine how galaxies were formed, observe the formation of stars, and measure the properties of planetary systems, both physical and chemical, including our own solar system. Not least of all, the Webb will carry on the task that underlies so much of humankind's activity in space, investigating the potential for life in other far-flung places. The 6,200 kilogram space-based element of the Webb will not orbit Earth, as Hubble has been doing. Instead, it will orbit the Sun. To do so, it must first travel 1.5 million kilometers, a 30-day journey to L2, the Lagrangian point at which the gravitational forces of Sun and Earth are roughly equivalent. Each orbit will take 6 months and keep the JWST out of the shadow of both Earth and Sun. Its trajectory also makes 24/7 communications possible. The Webb will stay in line with Earth as it moves around the Sun. And that is because, while the James Webb Space Telescope is looking for first light, its first task is to find darkness, the condition in which it can operate at its best. Three main component systems make up the space-based James Webb Space Telescope: an integrated science instrument model, ISM, the optical telescope element, OTE, and the spacecraft element. The key to the JWST's enhanced vision is its primary mirror, which measures 6.5 meters across. It comprises 18 segments made of beryllium, the lightest of the alkaline earth metals. A 5-layer sun shield the size of a tennis court will protect the JWST's dazzling array of specialist technology. As this orbiting infrared observatory continues the work begun by Hubble. On board are a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, a near-infrared imager, and a slitless spectrograph. The NIRSpec has micro-shutters, which will make it possible to observe up to 100 objects simultaneously. The Webb's cameras and spectrometers are capable of detecting extremely faint signals, a crucial factor in its attempt to see as far back as first light. While NASA busies itself with James Webb, its European counterpart ESA is hard at work on another related mission with a much more famous name attached to it. Euclid is named for the Alexandrian Greek whose geometrical study, the elements, formed the basis of our mathematical thinking for almost 2 millennia.
What we want is actually to continue our successful program, which is actually providing a cutting-edge space science, meeting the challenges of worldwide research.
But where the original Euclid worked only with ruler and compass, his namesake in space will have much more sophisticated instruments in its locker. Like the Webb, Euclid boasts a modest mission to map the geometry of the dark universe. Over a period of some 6 years, it will look back over the entire time in which dark energy has contributed to the accelerating expansion of the universe. Scientists tell us that what we can see accounts for less than 5% of what is there. The rest is made up of dark matter, some 20%, and the remainder of dark energy. They act in contradictory ways. Dark matter acts through gravity to play its role in forming galaxies and slowing the rate of expansion of the universe. Dark energy, on the other hand, defeats gravity and thus encourages acceleration of that expansion. The Euclid Consortium, part of ESA's Cosmic Vision program, brings together 1,000 scientists from 100 institutes in 14 countries, with added input from NASA in the United States. In 2013, Italy's Thales Alenia Space Group was named as prime contractor, with Airbus in France responsible for the payload module. On board Euclid's payload module will be a telescope 1.2 meters in diameter, a visible light camera, and a near-infrared camera and spectrometer. Euclid will undergo its critical design review in 2017, with its launch planned for December 2020 from Kourou in French Guiana. Like the JWST, it will orbit around the L2 point. Channeling the thinker whose name it bears, Euclid will be looking for genuine insight into the evolution of cosmic structures. Investigating the nature of dark energy, dark matter, and gravity, it will track their observational signatures on the geometry of the universe and on the cosmic history of structure formation. Euclid will deploy 2 key systems: weak gravitational lensing, or WL, and baryonic acoustic oscillations, BAO. WL examines how background galaxies are disturbed by foreground dark matter and measures modifications in the shape of galaxies brought on by the gravitational lensing of dark matter. BAO reveals the wiggle patterns which help us gauge the expansion of the universe, revealing the three-dimensional distribution of structures by means of the spectroscopic red shifts of galaxies and galaxy clusters. Putting it more simply, perhaps, Euclid's task, made easier by its unprecedented accuracy and stability, is to map the shape, position, and movements of 2 billion galaxies, or 1/3 of the sky. Even more excitingly, the James Webb Space Telescope is not the only star performer, pardon the pun, on the horizon. In 2016, NASA confirmed the decision to go ahead with its Wide Field Infrared Survey Telescope, or WFIRST for short.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time.
This new observatory will offer astrophysicists the best of both worlds by casting its eye both wide and deep as it seeks to shed light on dark energy, exoplanets, and cosmic acceleration. Surveying large areas in near-infrared light, a single image from WFIRST will have all the depth and sharpness to which Hubble has accustomed us, but will cover 100 times the area. In fact, a single image will encompass as many as 1 million galaxies. The new telescope's work will slip into the groove already made by Kepler, the Sloan Digital Survey, and TESS, the Transit Exoplanet Survey satellite. WFIRST will use microlensing rather than the transit method of detection. It will employ a 2.4-meter diameter telescope provided by the National Reconnaissance Office. But the best of both worlds part of the WFIRST story comes with the coronagraph, which NASA has been able to add to its instrumental array. This is a means of dimming the light from a so-called host star in order to see better the planet or planets orbiting it. And that is highly significant if we remember that the host star may be up to 1 billion times brighter than any exoplanet identified. If successful, the coronagraph technique will make it much easier to determine the chemical composition of planetary atmospheres. WFIRST will be able to use a unique deformable telescope controlled by computer. This first mission, due for launch in the mid-2020s, being what is called a technology demonstration, laying down a scientific marker for future missions to go in even more determined pursuit of life beyond the confines of our own solar system. While all of this is going on in space, Here on Earth, another agency will be tackling the question of dark matter from yet another angle. At CERN in Geneva, the Large Hadron Collider is now running at full power for the first time.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphoton. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV, and what is most important that these particles could be searched for at low energy experiment with fixed target experiment.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
So the idea is that when the high-energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high-energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
Might its scientists be able to replicate dark matter itself?